So we're going to go over 3 videos, which have 3 questions, each of which we're going to use the elimination algorithm for. Now, next week, we're going to start by solving the non-homogeneous system of equations using a slightly different technique to what we have here. Both techniques are valid. Whichever technique you find useful, I encourage you to use. Now, with the elimination algorithm, there are 3 main steps that we do repeatedly. First, locate pivot and make 0. Or sorry, make 1. Second, put it in the right spot. Third, 0 out the column. And we'll do this again and again. We'll locate the pivot, make it 1. We'll put it in the right spot, and we'll 0 the column. Now, there's something you should note about these 3 steps. Here, this step uses lambda rj places rj. This step here uses rj swap with ri, and this step here uses rj plus lambda ri replaces rj. So each of these steps in this process that we're going to go through again and again only uses one elementary row operation. When we make an entry 1, that's using multiplication. When we put in the right spot, we're using our swap. And when we 0 the column, we're using our addition of a scalar multiple of another row. Okay, so with that being said, we're going to go through our first example problem. And I've reordered it so that the problems are back to back to back. So we have our first problem where we said determine whether or not the set of vectors is dependent. Okay, so here we got to the point where we said we have a solution to the system of equations x1 plus 0, x2 plus x3 equals 0, 2x1 minus x2 plus x3 equals 0, and 3x1 equals 0. And we said a solution to this system of equations is a solution to this linear combination. And in class, we made an argument about how this is a general linear combination equaling the 0 vector, and we're trying to solve for the solutions that are all such linear combinations that equal 0. And the reason that we do this is if we can find a non-trivial linear combination equaling 0, it's dependent. If there's only the trivial linear combination, that means it's linearly independent. So once we have that, we ask ourselves, how can I solve this homogeneous system of equations? Or what is the set of solutions for this homogeneous system of equations? So remember, our steps are 1, find the pivot, 2, put it in the right spot, or 1, find the pivot and make it 1, 2, put it in the right spot using swap, 3, eliminate, and then we repeat this over and over and over again for each successive pivot. So if we look at our augmented matrix representing this system of equations, which we have here, the first thing I'm going to do is I'm just going to rewrite it down here. Okay, so 1, 0, minus 1, 0, 2, minus 1, 0, 0, and 3, 0, 0, 0. First, what we're going to do is we're going to highlight my pivot, which for this sake will be this entry, and we're going to make it 1. So step 1 complete. Check. Now, because it's the pivot, it has to be the first row that we're working with. And it is the first row. Check. So now I need to use it to eliminate the column. So I'm eliminating this column here. So I need to eliminate this entry and this entry. So I'm going to start by row 2 minus 2, row 1, replacing row 2, giving me 1, 0, minus 1, 0. And again, the third row doesn't change. So 3, 0, 0, 0. It's this middle row that's going to change, subtracting 2 of these off. Now, to calculate what that is, we're just going to do a little aside. We have 1, 0, minus 1, 0, minus 2 times, we have, sorry, let me rephrase that. We have 2 minus 1, 0, 0, minus 2 times 1, 0, minus 1, 0. And this is the first, this is row 2 minus 2 row 1. And we can figure out what this subtraction is. So this would give us 2 minus 1, 0, 0, plus negative 2, 0, 2, 0. Now adding these gives us 0, minus 1, 2, 0. So that's what goes in this row. 0, minus 1, 2, 0. Once again, I can do row 3 minus 3, row 1, replacing row 3. And here the first row doesn't change. The second row doesn't change. My third row is going to be 3, 0, 0, 0, minus 1 time, or minus 3 times 1, 0, minus 1, 0, which is going to be 0, 0, 3, 0. So this becomes 0, 0, 3, 0. And now I've zeroed out the column. Check. So the next stage is that we're going to pick the next pivot column for this row. And we can't use this first column anymore. Once we've used or first row anymore. Once we've used a row to make a pivot, we can't use that row again. It's fixed. So the remaining rows, we have to pick a pivot from. And what we do is we work ourselves across the column and we find the next available pivot. So if we go from the first column to the second column, now we're looking at these two entries here. We're looking for non-zero entries in the remaining entries of the column from this second row down. And there is one. There's this entry here. Okay, that minus 1. So that is going to be what we choose to make our pivot. And remember, our step is we make it 1. So now that we've chosen our pivot, which is here, we need to make it 1. So we need to take minus 1 times row 2 replaces row 2, giving us 1, 0, minus 1, 0, 0, 1, minus 2, 0, 0, 0, 3, 0. We got that because minus 1 times 0, 1, or 0 minus 1, 2, 0 equals 0, 1, minus 2, 0. You expand that constant into your vector. Okay, so now we've made it, we've picked the entry and made it 1. If we look up and down, we've zeroed out the column. We've put it in the right spot because it's the next row, first entry, it's in the right spot, and we've zeroed out the column. So now we have our last entry. Our last entry is this 3. Remember, we have to go only from rows that are below what we've fixed already or where we've picked our pivots. So the only entry we could have is this entry here. And notice that that entry is non-zero. Everything before is already zeroed out, so we only have this non-zero entry. So our steps are first we make it first we make it 1. So what we're going to do is we're going to take this and make it 1 by taking R3 and multiplying it by 1/3 R3, replacing R3. So by multiplying by 1/3, we get the following augmented matrix. Again, the first 2 rows aren't touched, so they don't change. And now 0, 0, 3, 0 multiplied by 1/3 is 0, 0, 1, 0. Now that it's in, so we've done our first step of making it 1. Now putting it in the right spot. It is in the correct spot. 2, the last thing we need to do is zero the columns. So we're going to take R1, add R3, and replace R1. We're going to take R2, add 2 R3, replace R2. Note that these are actually independent of each other. Adding something to row 3, and then using the same vector and adding row 3 to row 1 and adding row 3 to row 2, we can do those independently. It doesn't matter the order we do them. They're not going to interact with each other. So we're allowed to do those in any order, and we can state that we're doing them at the same time. And this gives us 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. So I encourage you to do yourself. Well, what does this tell us? This is in echelon form. Satisfies the conditions of echelon form. Everything's down to the right. Columns are all zeroed out. And it gives us the system equations x1 equals 0, x2 equals 0, and x3 equals 0. Thus, the only solution is the trivial solution. Therefore, the only linear combination equaling 0 is the trivial linear combination. Therefore, as 0 is represented uniquely, the set of vectors is linearly independent. Remember, now that we've solved our system of equations, we need to answer the question that was asked. Here is asking if the vector is dependent or not. We had a system of equations, we set it equal to 0, and we showed that the equivalent system of equations is simply the 0 vector, meaning that the only linear combination equaling to 0 is the trivial linear combination, which is quite interesting.